Okay.
Clear?
Yeah, it's just, I'd say don't get any smaller.
Okay, yeah.
But yeah, I think it's, yeah.
Nobody says?
No, nobody has come yet. Interestingly, they'll come. I don't think I've done anything different. Yeah, usually at this point, somebody starts.
Is it the same meeting?
Yeah. Everything is as usual. So, there you go. There's the first. There's Sonia. And then okay. Hello, Antonio. Hello, Kelly.
Hello.
Hi. Stick my head. Ah.
This is the second one.
Right. Good. Hey, hi, Andrew.
Hello.
Yes, so there's just 2 people missing. Let's wait another minute. Harrison and Hassan. Okay, everybody's here. Okay, yeah. Okay, well, good morning, everyone. Or good noon. So everybody's here. We have 5 people online. We have Navjeet as well, and we have Muhammad. So today we'll wrap up chapter 9. Last time I discussed the motion of massive particles in the Schwarzschild metric. And of course, also very interesting is how massless particles, how light would propagate in the Schwarzschild metric. And today Muhammad will tell us about it. If you haven't seen it, Muhammad's notes are also on the campus.
I sent them by email.
Sorry?
I sent them by email.
Oh, you sent them
Yes.
by email. Very good. Okay, so everybody has the notes. So yeah, go ahead, please.
Okay, good morning. Good afternoon, everybody. I hope I will be clear in this lecture. I will talk today about light rays, orbits, deflection, and time delays for the light signals near massive objects. The calculations for these to find these things the same, just the same like the calculations for the massive particles, but with one main difference, which is the normalization condition, which is u dot u will be 0, which is not -1. It is not -1. Now we will use always u dot u is equal to 0. And we will use the line element from with the Schwarzschild Schwarzschild metric, which is ds square is equal to -1 minus 2m over r dt square plus 1 minus 2m over r minus 1 dr square plus dr square r square d theta square plus r square sin theta square d phi square. And we have 2 constraints, which are the conservation, 2 conserved quantities. The first one, which is E equal to minus zeta dot u, which is equal to 1 minus 2m over r dt by d lambda. Also, we have L, which is equal to eta dot m, which is equal to dot u, which is equal to r square sine square theta d phi by d lambda. We have the killing vectors, which are theta, which is 1, 0, 0, 0, and eta, which is 0, 0, 0, 1. And these relations, as we know, are related to the conservation of angular momentum and energy. Now, simply, we need to use this line element with these conditions. And we need to be clear that because we have conservation angular momentum, we have a motion just in a plane. So we will use theta is equal to pi over 2, just as we use it in the particles case. And in this case also, d theta will be equal to 0. So we don't have this term. This sine theta will be equal to 1. So the line element now, what we have, ds square is equal to -1 2m over r dt square 1 minus 2m over r minus 1 dr square plus r square d phi square. Okay. Now, using the 2 constraints, we can find, we need to use dt by dt, we will apply it here. by we need to use this constraint, and for the and use this condition, the normalization condition, u dot q is equal to 0. In this case, we have dtt dt by d lambda square plus grr dr by d lambda square plus g phi yes d phi by d lambda square is equal to 0. Now we can use dt by d lambda from this formula and d phi by d lambda using this formula. And we will in this case we will find that minus 1 minus 2m over r dr. No, this is the time minus 1 plus 1 minus 2m over r dr by d lambda square plus L over R is equal to 0. We need to reorganize these terms. Then we will find this relation 1 over L R E. This is yes. By reorganizing, we will find this 1 over R square minus 2m by R cube plus 1 over L square dr by d lambda square. We put this term L over R because we will define it as 1 over B square. We define
it's L over E, not L over R.
Over B, yes, over B. Sorry. We define B is equal to L over E, and we will find it later. It will be the impact parameter. As we see also here, if we need to compare it with the particle case, we have this equation from the previous lecture. We have E squared minus 1 over 2 is equal E squared minus 1 over 2, 1 over, just 1 over 2, minus m over r plus n square over 2r square, m l square over r cube plus 1 over 2 dr by d t or tau plus tau square. We can see from the previous time that this term and this term are related to the maybe total mechanical energy. We can also this term can relate to the effective potential term, this term or this term, and this term can be related to the kinetic energy, but we don't have any kinetic energy in our case. Also, because of this condition, which is the normalization condition, u dot u is equal to 0, we don't have this term in this equation. Because of that, we can take L as a factor between these two terms and put it in this equation on the other side. Previous time, we can find from the previous time we could find the trajectory of the particle and any other properties of that motion, and it was depend on the mass and the energy and something like that. But in this case, in our case, the trajectory for the light ray will depend on the ratio on L, which is L over E, which is the impact parameter. All the properties and the calculation will depend on this this ratio. Also, we can see here, we have it, 1 over b squared. When we take 1 over b, we have the square root of the other side. It will be positive and negative. Positive and negative, it will give us the direction of rotation of that ray about the source of the potential. If it's like this, it is counterclockwise, then L over B is positive. If it is in the opposite direction, then 1 over B is negative. So the positive and negative sign here has a meaning. Okay, we can now find B, which is the impact parameter. As always, scattering calculations, we have a coming ray, and this ray is bending, and it is away from the axis of symmetry by D. This is the minimum, or the turning radius. We can name it R1. And we can see that this is the total angle. We need to name it delta phi. No, I'm sorry. This is related to ray bending. This is for the next part. Now for a ray coming, and this is the radius R. This is the axis, maybe it is Z axis, we can name it. So this is X, which is equal to R, and this angle is phi. R cosine phi, and this component is Y is equal to R sine phi. For large R, or R is a ray coming from infinity, so R is very big. And for large R, we have sine phi is equal approximately to phi, which is equal to D over R. And we have the, I need to write them, we need to use them always. Now, we need to find L over E, which is equal to L. We know it from the constraint L is equal to R squared d phi by d lambda, and we have E is equal to 1 minus 2m over R d t by d lambda. If we take them and divide them, L over M, we have d phi by dt. We can remove this dependence. And we have R squared over 1 minus 2m over R. For large R, which comes from infinity, this term will be 0, and we have just 1. And in this case, we have just d phi by d lambda R squared. By using the chain rule, d phi by dr, dr by dt, R squared. Now, for large R, we can assume that R in the same direction almost of the incident ray, and its velocity is minus c or minus 1 because it is decreasing. So we have here minus 1. We have here R squared. d phi by dr from here, d phi by dr is equal to minus d over R squared. So this ratio L over E is equal to D, but we define it from before as B. So it is the most important, or everything depends on this ratio, which is B. And this B is has a dimension of length. Okay. What about the effective potential? Now, the effective potential is equal to 1 over R squared minus 2m over R cubed. And I'll draw this. I will discuss now just the case of the GR study. I will not take the classical. We have, this is 6m, this is 3m, this is 2m, okay. I will need to compare it with the particle case. We have, I don't know if the color will appear or not, but I'll do it. It's maximum at 3m. Here we have a maximum at 2m, and the minimum here. Yeah. Okay. This is light ray case, and this is the particle case. This is 6m. We have the minimum, and also we have a circular orbit at 2m. But in the light ray case, we have a circular orbit at 3m. In this case, 1 over b is equal 1 over b squared is equal to 27m, I think, yes, m squared. Okay. Now we know from the particle case, we have a scattering case, or we have a bound case with the elliptic orbit, or with a circular orbit about with the R minimum, which is the stable, and also this R, which is unstable. But in light ray, we have just one case, and in this case, the light is unstable in the radial, in a circular motion. So, where is my? Now, if we have a light ray with 1 over b squared less than 27m squared, then this light ray will scatter about this this mass. It will not be captured by this mass. But if the light ray 1 over b squared is equal to 1 over 27m squared, then it will capture by this mass, and it will start rotate in a circular motion with R equal to 3m. Any small perturbation will maybe it will be captured or will scale again. Any light ray come with 1 over b more than this value, it will start rotating and captured by this potential source. Yes. Now, this is the case when the light is coming from the infinity to the source. What if we have the opposite case? If the source is a source of that light, and the light will be emitted from between from a point between 2m and 3m, just what we do in the previous lecture. In this case, if the radial component, I'll draw, this is the source, this is the mass. If the radial component, we have 2 points, which is 2m and 3m. If the radial component of the scaling light signal has this condition, 1 over b is equal to 1 over 17 m squared, then the light will scale. But sometimes we have different components, or we have a signal in different angle, and we need to name this angle by psi. So we have 2 components for psi. We have, this is the direction of the velocity for this signal. This is u sine psi, and this is u cosine psi. And simply psi is, or tan psi is, yes, this is u in tangential component, which is in phi component, this is u phi divided over the radial component of the velocity, ur. In this case, we can find such a psi, and this psi is a critical angle. If the for psi critical, if the ray has psi less than this angle, then it will scale. If psi is more than this angle, then the ray will recaptured again by this mass. We can compute it now. This is an example on page 209 and 210 in the book, computing the critical angle. And in today's lecture, there are maybe 2 or 3 integrals. They are difficult and long. We just take the final result of them also with using the approximation limits. Okay, now for this example, if there is a mass, okay, if we have this example, if there is a stationary observer away from the mass, from a star or a planet by 2, in a distance between 2m and 3m, so just as our case, and he send a signal flight in all directions in phi plane, or in theta equal pi over 2 plane, this plane, and this signal in all directions. So some of this signal will escape, but some of the components of this signal, or the rays of this signal, will be captured again to the mass. So we need to find out the critical angle by using the last formula, which is tan psi. We need to be psi critical now. It is equal to u phi over u r. But as we know, u phi will be equal to G5, find D5 by D lambda, and I will write it. Look in phi direction, the unit vector divided by GRR UR, which is okay. From that, we have the final result of phi. It is psi c. I'm talking about psi. Psi critical, which is equal 1 over r for that mass, 1 minus 2m over r, 1 over 2. M square minus 1 over r square, 1 minus 2m over r.
So can I ask, what is the condition that you used to determine psi critical?
We have first, we have E phi is equal to 0, 0, 0, 1 over r, and we have E r I will see if I
Yeah,
I don't.
yeah, I don't
This
see it
is
in the
really in
notes.
the.
I just thought maybe you remember.
No,
You know,
no, it is
how do you
really-
say, okay, how do you decide it's going to escape or it's not going to escape? What's sort of the initial condition, and then you go through the calculation. And you
Yeah,
get
I
to
don't
this
know.
result,
I'll
right?
take it
Okay.
as
okay.
it used from the textbook. So we have two limits now. We have R for the position is bigger than 2m and less than 3m. Between the two limits. Throw them here. At the end, it is light signal has velocity. This is 2m and this is 3m. We have the light signal from. Now, for the two limits, if r at 3m, then psi c, maximum psi c, will be pi over 2. So any tangential signal to this surface will scale. For this limit, this is the maximum limit, psi will be 0, psi c is equal to 0. There is no any components of this light signal will scale. All of them will be captured again to the source. Between them, between these two limits, we have the psi critical will start decreasing like this. This is psi critical at this point, for example, and this is psi, it is bigger here. Psi critical at this point, further than this point. Yeah. Now we'll talk about deflection of light. Now, any source of mass will bend any moving particle near it, and it is always happen for, and also it is happen for light rays. And measuring this bending or deflection for the sun is was I think it's the first test of general relativity in 2019. 19, yes. 19. Okay. Also, that deflection of light it is the mechanism to understand the gravitational lensing by huge objects in the deep space. And the light trajectory can be found, and it is depending also on on B, which is the ratio L over E. We need to use it again. Okay, now we'll use to find the formula between R and phi, the formula of the trajectory of the line. It is a formula of R of phi, or 5R, just as we did for a particle in classical mechanics. Now we'll use the relation 1 over B squared is equal to 1 over L squared dr by d lambda squared plus the effective potential. And we need to use the condition for the condition that contains the phi in it, which is the conservation of angular momentum at theta equal to pi over 2. And L is equal to R squared sin theta is equal to 1 d phi by d lambda. Simply, we need to organize this dr by d lambda is equal to plus minus 1 over B squared minus D effective multiplied by L. But L is equal to R squared d phi by d lambda. Oh. Now we can find dr by d phi, or phi as a relation of R. So we can find that d phi by dr is equal to plus minus 1 over R squared E over L squared minus 1 over R squared plus 2m over R cubed. Putting R here, dr here, and finding the integral. In this case, let us see this scattering or deflection case. This is D or B, which is the impact parameter, and this is the R minimum, which is R1. And the light ray will change its direction by this angle. Let us name it delta phi. Yes, delta phi. And we have this angle. We can name it delta, small delta phi, which is equal to capital delta phi minus pi. We need to find this phi, which is the deflection angle. Also at R minimum, we have, this is the minimum value. At this value, dr is equal to 0. And we have, from this equation, that 1 over b squared is equal to v effective. To solve this equation, we need to assume this, to define this quantity, which is R is equal to B over omega S. And we need to take the limit for small m over B. Finding this integral will give us this relation or this approximated value for the total delta phi. This will give us delta phi, and it is given in the book. It is equal approximately to pi plus 4m over b. Yes. We need to find delta, which is the angle of deflection, which is delta phi, which is this value minus pi, which is equal approximately to 4m over b. This value for sun, for the sun, which has m, I think this is the sample, and for air, I will use m plus inside the circle. For the sun, delta phi is equal to 1.75 seconds, I think, yes. For a light coming inside, just at the edge of its radius, of its surface, it will be deflected by this small angle. I have just like a question or something like that, which is, what if we need this angle to be 2 pi? We have this mass, and we have this is the light, and we have this is no pi, not 2 pi. It is 2 pi. It will be in the same direction. We have delta phi is equal to pi. Then the ratio m over b, it will be equal approximately to 2 multiplied by 10 to 27. It is very big to be to do this angle, to deflect this angle. That's all for light deflection. Now I will find the time delay for a light signal.
So
yeah,
according to the numbers you noted here, so that would be an object that's 1,000 sun masses or something like
yes,
that.
It is
or 10,000.
10,000. Yes, I computed it for sun. For example, if we need to make the sun to do this angle, we need to increase its mass by 10,000 times.
Oh, yeah.
Yeah.
Wow.
I don't know about this. Maybe the space students know more than me. Maybe we are here.
Mohammed,
Yeah.
there is a comment in the chat on Zoom.
Oh, sorry. Let's have it. Sorry. Have a look.
Sorry.
Yeah, I wasn't paying attention. Oh. Kelly says internet's wonky. Kicked Andrew out. Okay, maybe we hope we'll be back. Okay, good. Okay, thank you.
I have one question.
Yeah.
So, when you were discussing the impact parameter to find out if the light ray would be trapped in an orbit or it would escape or it would spiral inwards.
Excuse me again.
So, when you were discussing if the light ray would orbit around in a circular motion or elliptical or it would spiral inwards or escape, you defined it using the impact parameter, the condition, right?
Yeah.
1 over b squared, 1 over 27m squared. So if that condition is satisfied and the light ray starts to orbit around the mass distribution. Is the angular velocity the same as it was in the case of a massive particle orbiting the social geometry?
I think it will be different. But it did compute it, by the way. The rotation around that particle.
Yeah, the angular velocity. Because the metric isn't really changing, right, Professor? Does the angular velocity only depend on the metric we are considering?
No, but it also depends on the characteristics of the fore velocity, right? On whether that's U value is -1 or 0.
Yeah, it's 0 now.
So I would expect it's different. Even the radii are different, right? So I would be very surprised if there was a simple relation. I don't know.
Okay. Again, now what if we have a circle? This is star 1, okay? What if its light go away and return back by a massive object and we observe? Is this heaven or not? I don't know. So we can count more stars than the. Now the delay of light, we will take two cases. We will take the classical case and the GR case, which is observed in 60s. If we have a mass, which is the sun, and this is the earth, and we have a straight line for a light signal. This is the classical case. And we have a reflector at this point, in the other side of the sun. And this light signal is reflected. This reflector R, capital R, maybe it is, and it was really a satellite near Venus and Mars, and the trip going and go back, it is about 41 minutes. If we computed, the satellite will be at Mars orbit on the opposite side of the sun. The time delay observed by Shapiro in 60s, and he computed this time delay, and the computation is the same, almost the observed delay. And this is the fourth test, the fourth main test for general relativity. And if we have, this is the sun again, and this is the earth, and we have, this is the reflector here. Okay. We have that two trips going away from the earth to the reflector and coming back signal. Now, we have for each trip, classical trip and the observed trip, we have different times. In classical case, by computing the triangle identities, and this is the impact parameter, which is R1 equal to B, which is the closest distance from the sun. And we have the distance from the reflector to the sun is R, capital R, and the distance from the sun to earth is RA. And we have these two parts, which are the square root of R earth square minus R1 square, and R1 is very small, smaller than this distance, then we will use this as an approximation in the calculations. And we have R of the reflector square minus R1 square. Here we have just this known value, which is R1. Now, in the classical case, we have a time for the trip, which is 2 multiplied by this all distance. So the time here, you can name it delta t, is equal to 2 by this square. I have it already here. Classically, delta t is equal to 2 multiplied by this distance, which is multiplied by divided by the square of not the square, the speed of light, which is c, which is equal to 1 r reflector square minus r1 square plus the square root of r earth square, the distance from the sun, minus r1 square. But the observed value and the computed value, which is the actual one for this trip, is delta t total. This is the actual or major, you name it. We need to find the time delay between these two periods. We need I need delta t axis is equal to delta t total minus the classical value. Okay, the trip will take 41 minutes, I'm sorry. The Earth in its orbit, it will not pass too much distance in this period because it needs 365 days to complete one orbit, one rotation, yes. And I will use again 1 over b squared, which is the impact parameter, which is equal to, again, 1 over L squared dr by d lambda square plus v effective. And I will use this condition, which is the conservation of energy constraint, 1 over 2m over r dt by d lambda. Now, I will find the relation between t and r, just as what we find a relation between r and phi in r5 plane. Now I will find this relation between r and t in rt plane. Now, by using these two formulas, we have dt over d lambda is equal to e 1 over 2m over r to minus 1, and also I have the r by d lambda is equal to plus minus the square root 1 over b square minus b effective multiplied by L, 2 or 1/2. Just divide them over each other, then we have dt by dr is equal to plus minus 1 over b, 1 over b square minus b effective over minus 1/2, also 1 minus 2m over r to power to minus 1. Now, plus minus signs. It is a relation between r and t. We need to divide this strip to 4 parts. If the R by dt is decreasing, then it is negative. Yes, this is fine. Then the light signal is coming to our point of reference is the sun. So if the R by dt or dt by dr is negative, then the light is coming toward the sun. If it is positive, then it is going away from the sun. So we need to divide this strip to 4 parts. 1, 2, back 3, 4. By that, the integration, I have it also ready. T as for general R, T from R1, which is the minimum value, to any point R. Then we will take the R and the two limits, RA or R this and R, oh sorry, small R, and we have R reflected. Is equal to this integral. R1 to R, dr1 over p 1 minus 2m over r to minus 1. Also 1 over b square minus d effective or 1 half minus 5. Also again at R1, which is R minimum, we have B is equal to 1 over B square is equal to B effective. And we need to take the limits where for the solar system, we have M. Where's the in our solar system, we can approximate these values for M for the sun to the first order. In this case, we have B will be equal to R1 minus M, and B square will be equal also to R1 square minus 2M R1. And the result for this integration, it is written in the book. T as a function of R and R1 is equal to square root R minus R1 square plus 2M ln R plus square root R square minus R1 square over R1 plus M R minus R1 R plus R1 to the power half. As we see, from R1 to R, from R1 to any R, the first term is the classical term, which is the square root of R square minus R1 square. And these two terms, they are positive. If we check them, they will make the time more than the classical expected time. Now for small r, R1, we can take the big R, which is R, from here and from here as a factor, and then we can find that T of R and R1 will be equal to here. R plus, because when we take R outside from here to be R 1 over capital over R, which is the big, then this term we can cancel it. It will be square root of 1. Also, we have 2m ln 2R over R1 plus M1 minus R1 over R. We have two limits now. We have R, the radius or the distance for the Earth from the Sun, and we have the radius for the distance for the reflector from the Sun. So we can find T for R between R Earth and the smallest R1 is equal to R Earth plus 2M ln 2R Earth over R1 plus M1 minus R1 over R for the Earth. Also for the reflector, we have R1 is equal to R for the reflector plus 2M ln 2R for the reflector over R1 plus M1 minus R over R reflector. Yes. We need this strip is between R1 and R and or R1 and R for the reflector. We need it for 2 times for each one. So we need delta T now. Delta T total. It will be 2 from this and 2 from this. So it will be equal to 2. We need to add them together. 2 R for F plus R for the reflector plus 2M, it will be 4M ln. If we add these together, they will be 4, I think. Yes, 4 R F R reflector over R1 squared. Also, we have 2 of these things, which is 2M. We can take R1 over RF, R1 over R, RF and R reflector is 0. So we have just 1. This is, we have then 2M. I'll put it here. Plus 2M. Our value, what we needed, is small delta, which is we need delta T axis, which is equal to this minus the classical value, or the classical value. Classically, we have the time is equal to 2 R of R square root 1 over R1 over R squared plus R for air 1 minus R1 over R air square. Again, we can cancel this term and this term. Then we have just the relation delta T is equal to 2 R for the reflector plus R for the air. We need to remove this time from this. So that will cancel with this. So the total or the net time is 4m length for R for the earth, R for the reflector over R1 square plus 2, which is a positive value. So we have a delay, and this delay is measured and is computed by Shapiro, I think. What's the name of it? Shapiro, yes. I'm not good at names. And this time delay is not because the speed of light is less at this region, but because the space-time continuum here is compressed, and the definition of 1 meter and 1 second is changed, and because of that we have a net time deviation. And that's all for this section, and thank you. Any question? I finished.
Oh yes, you had. We still have.
Yeah.
You had 10 minutes to spare, right? Yeah. I thought you would run out of time, but you went through it nice and fast. Yes, that's great. Thank you very much.
Thank you.
Yeah. So, any questions? There's applause from Kelly. I can do that too. There we go. And Antonio and Hassan. Okay, everybody is applauding. Right. Yeah. So, I mean, maybe a remark or two remarks I had. Well, so one remark is simply that these are, of course, all the kinds of things that one has to take into account when one constructs the GPS. Right? They're not they're small effects, but they're significant enough to be needed to make the GPS work. Because if you just get these time delays, if you don't put these time delays in, then after a short while, the whole system will be off, and I won't be able to correctly calculate the distances and the positions anymore. Right. Yeah. The other remark I had earlier on when I asked the question about the critical psi, the condition was simply this. Remember, we had the radius 2m and the radius 3m, and we were emitting from here somewhere, and the question was, okay, there's an angle, so there's a range of angles for which light rays will still escape, and then for if you use a smaller angle, then they will fall back in. And yeah, the answer was simply you had an expression that the tangent of psi, psi being, I guess, this angle or something like that. Yeah. You had a general expression just from the equations of motion, containing L and E and all those different things. And right, to find the critical one, right, and so this equation in general contains some 1 over v squared somewhere. And to find the critical one, you simply insert this condition. Remember that there's this critical value of 1 over v squared. That's 1 over 27m squared. So if you want the critical value, then you set this just to the critical point. And so somewhere in your equation you have this, and then that's the condition. Yes. That you set it to the critical value. And so I at that moment it also wasn't clear to me, so I had to think of it. But yeah, there's always this one critical value that determines whether you're just at the peak here, at the threshold of this effective potential, whether you make it over or not. So yeah, so those were my two remarks. But yeah, questions? Further questions?
Yeah, I had a question regarding the, I guess, a deflection of pi. So so the light ray goes back in the direction that it came from. I guess maybe it's not clear to me, but how does that? How do we know that the impact parameter stays above 2m in that case? Because
Bit better.
I mean, well, so I guess that's my question is like, if it's smaller than 2m, then it's it falls into the black hole, or into the mass. But can the space time be distorted enough such that that's the geodesic that it travels while still being outside of the that 2m radius?
So obviously, the geodesic has to stay outside that radius because we know what happens if you go inside. You can't get back out anymore. So one could, of course, ask, do we see that in the expressions? And I'm not sure. Maybe did I leave your notes somewhere? Maybe do you have the answer, Mohammed? Or
No, I'm just asking.
okay, let's see whether we have the expression here somewhere for the deflection. So that's probably page 7, right? Page 7 or 8. Let's see whether we can see this. So does that go into the direction you're aiming, Harrison, or are you aiming at a more specific point?
That's that's the section I'm considering because the larger the impact parameter, right, the less the photon deflects. Right. So for it to deflect all the way around, the impact parameter would have to be still greater than 2m.
Yes, it would have to. The question is, can we see that simply, or is it hidden somewhere in the intricacies of that integration that one has to do?
Right.
So one formula we have here is the one on page 7. Let's see. So that right, and the R1 is, of course, the R1 is the distance, is the closest distance. So that would have to. So the hope is that we can see that this has to be larger than 2m.
It's between 2m and 3m.
Sorry.
Between 2m and 3m.
Between 2m and 3m, you say.
Yeah.
I can't have a deflection by pi if I come from outside. Right.
I don't know. I'm asking.
Okay. Then let's explore this. Okay. Well, let's draw something. So we've got this effective potential. This is 3m. Somewhere here, there's 2m.
In the book, they draw more than 2 pi.
Okay.
They draw schemes for deflection more than 2 pi.
Yes, and indeed, that is possible. So, right. In Keplerian, if you're doing the pure classical Kepler orbits, you can't have a larger deflection than pi. You can come straight back, but no further. Right? If you're doing a Kepler problem, you can come in. Yes, that would be the parabola. And I think for the parabola, you approach angle pi. You're coming straight back out. But if the potential here has a different dependence than the Kepler potential, you can get any angle. You can have trajectories that do this.
Yes. Yeah.
And then go back out after 10,000 radians, degrees or radians, or whichever way you want. So yes, that can definitely happen.
So to play a role of mirror.
Sorry?
Just to be like a mirror.
Well, we're asking, to reflect. It depends very delicately on your impact parameter.
Yeah.
So it's not like this thing is a mirror for any particle coming in. It only will reflect it only will reflect back for very special values. Right? So it's not, in that sense, it's not really like a mirror. No, but you can have one that goes like this.
Yes.
Right. So that's not what a mirror does.
It's just
I was trying to understand your analogy. So, but first, so. Anyway, we can have, I agree with you, we can have any angle. As soon as the potential isn't Kepler anymore, you can have any angle. But here I think the question was, what about the angle pi? And so, right, I mean, we are interested in a scattering that's coming in from infinity, as we're writing here in this formula. There are, no, right, if you're coming from infinity, then I think if you make it past this point, and you still have a component of the four velocity going inward, then you will be captured.
yes.
Right. So the best you can do is you can inject yourself into the circular orbit here. But if
It needs to be just a little bit less than the top.
Right, exactly. So we're talking here about the trajectories that come to somewhere here. Right. That's right. So it's not in this region. It's in the outside region. And time is running. But anyway, so let's look at this expression here that we have. Squared over L squared. Maybe we can see something. I'm not sure. I don't know whether I have the complete answer for Harrison. Let's see. Do we have anything more specific? No. So this is the one we're going to have to look at. And so, right, if I want this to be pi, or well, let's ask the other way around. Certainly, if my integration here starts at 2m, then of course it starts at this singularity. Then it's 2m over 2m. But there's of course this factor here. Not quite so simple to see. No, but right. Yeah, okay, so here anyway, now we have the question, are we talking about making it just to 3m? Right, if you make it to 3, right, the singularity should happen when you make it to 3m, because if you make it to 3m, that's when you inject yourself to the circular orbit. Right, so that's the almost the more interesting threshold. If you make it to 2m, you're a goner anyway. If you make it to 3m, you just inject yourself into the circular orbit. If you want to just come straight back out, then you have to be a little bit short of 3m. And this expression doesn't look to me like it's obvious what happens at 3m. It would have to be somehow doing this integral in the region around 3m would need to tell you that something drastic happens. But it's not obvious. So what I would do is I would expand the R in 3m plus something small and expand the whole expression and then see whether I see something there. But yeah, it's too complicated for me to answer, Harrison. That's the conclusion. But these are interesting questions. So those would be interesting exercises to see exactly, okay, what would it imply to get the scattering angle pi, and how close are you getting to 3m? Where exactly is it? But we can be sure, as you said at the very beginning, we can be sure that the turning point here is larger than 2m, and I would say it has to be larger than 3m. But that in the end, that has to come out of this expression, and it's too complicated to analyze just quickly like that. But that would be a nice exercise. Hey, I still have a homework sheet to come up with. At some point. Okay, yeah, so, yeah, sorry, I can't give a more concrete answer, Harrison. Do you have a follow-up question? Is there a particular point that one could still think about?
Yeah, I think you made an interesting point about the difference between 2 and 3m based off of today's discussion, because so that critical angle for escape is just for the particle to be able to come back out. Any phi that's less than that will stay captured. So any impact param. So by definition, the shortest distance right from the object is when the trajectory is perpendicular to that radius. So that means inside 3m, any trajectory will stay captured.
Right, because, yeah, exactly. Yeah, that's a good point. At the turning point, you would be tangential and you would be violating that critical condition once you're inside. Yes, I think that's right. Yeah. Whereas at 3m, you exactly eject yourself. Once you're further in, yeah, we're talking about the angle of psi that Mohammed defined, the angle of psi being equal to pi halves. And the value pi halves is exactly still at 3m is what gets you into the circular orbit. And any place further in pi halves is already beyond the critical value and you get captured. Yes. Yeah, I think that's right. Okay, so yeah, time has run out. Very good. So, Will, thank you again, Mohammed. We'll meet again on Monday. So I'll go through. I will say everything I want to say about chapter 12 on Monday, and then we'll have enough Jeet to talk about the Kerr geometry, which is the spinning black hole, on Wednesday. And so by doing that, we will have already recaptured that half of the week that we need. So we're on target. I'll find the other lecture somewhere else. But yeah, so that's it for today. It was good to have this first student lecture. and we'll have more in the upcoming weeks. And so at some point, as I just mentioned, there will be a homework sheet, but it's not very urgent. I'll try to give people the time to instead prepare their talks for the most part, and then at some point maybe I'll come up with the homework sheet. Yeah. Okay. So I'll see you all on Wednesday.
Can I ask one question?
Yes.
So in E&M, if you have like electromagnetic waves in medium, you can have the index of refraction be functions of the wavelength of the light.
Yeah.
In which case you can get like these dispersion relations. Can stuff like that happen for this? Like, can this lead to diffraction in any way? Or is it just it either escapes or it doesn't? All wavelengths either escape or they don't.
Yeah, I wonder. Because in principle, so it didn't appear anywhere here in an obvious way. But of course, the frequency of the light is encoded in the 4 velocity, right? So somehow, wouldn't it be in here somewhere? But I don't have a quick answer. I don't see anybody discussing dispersion here. But in principle, I don't know. That's a great question. Maybe not.
Maybe not.
Yeah, I'll think about this. It's a good question. But I would have thought that somehow the 4 vector of the photon does know about the energy. It does know about the frequency, therefore. And so you'd think that maybe in this parameter, there's some knowledge of that. How, on the other hand, well, I think Muhammad sort of brought out a nice scaling argument. Everything, right? These whole light trajectories depend only on this ratio. They don't depend on the energy separately, and that's partially, well, there is a d lambda somewhere, or d squared, and a 1 over L squared in front. These are the 2 types of places where the conserved quantities appear. And you say 2 things. You say, first of all, here I have only the ratio, and here I have the freedom to rescale the affine parameter, such as to put the L inside the lambda. And I haven't changed the physics. I've only reparameterized the ray. And that's why one says, actually,